Well, pre-calculus classes, good morning, good afternoon, or good evening. Much like in Chapter P, in Chapter 1 we are going to kind of skip around and only cover certain sections out of it as well. In Chapter 1 we start with Section 1, 2, talking about functions and also some graphing topics. So we're going to talk about the difference between relations and functions, and certainly talk about domain, range, and some other topics as well. So, a relation is any set of ordered pairs. Domain is all of the x values, so I actually kind of like to even add that in. You may see or hear domain referred to as the inputs of a function. It's always the independent variable or the first component of an ordered pair. Range is your y values. It's also the output, the dependent variable, or the second component of an ordered pair. And then a function is a relation that maps each element of the domain to exactly one element of the range. We'll actually talk about what this means as we look at some examples. So, if we talk about, first off, example 1 here as to whether or not it is a function. You know, one of the things that if you look at both example 1a and b is the key thing that is different. In example 1a, you have two values or two inputs pointing to one output. In b, you have one input pointing to two outputs. So that is actually a relation. This one is a function. So the problem here is you have one domain input mapping to two outputs. Here we have two inputs mapping to one output, which is actually fine. So another way to determine if something is a function is using the vertical line test. And again, one of the things that you certainly might see as an abbreviation moving forward, if you ever see VLT, vertical line test, but if any vertical line can intersect a graph in more than one point, the graph does not define y as a function of x. So you can certainly look at things algebraically as well, which we'll kind of talk a little bit about how to determine if something is a function. But if we subtract the x squared over, just to kind of talk a little bit even about the whole vertical line test, is if we have 1 minus x squared, when you graph that, let me reset our window, you can see this is a function. Now, if in this one we add the x over and square root it, and we go back in and enter both components, it actually is now a sideways parabola, which is not a function. So this one is a function, this one is a relation or not a function, whatever you want to look at that as. And basically the way you can always determine that is when you have y to the second. If you have an even power of y, that's not going to be a function, whether it's y squared, y to the fourth, and so on. So again, talking a little bit about whether graphs are functions or not, vertical line test, you can see this one is not. For one like this, no matter where I would draw a vertical line test, I will never cross the function in more than one point. So this one, yes, is a function. This one as well, again, no matter where I would draw a vertical line, I will never cross this graph in more than one point. So those are both functions. This one is not. That's basically what I just showed you even on the graphing calculator. As far as function notation, when you see this, again, when you see the f parentheses x, that is read as f of x. X is the input, f of x is your output. So if f of x is 3 minus 2x, then f of negative 1 is 3 minus 2 times negative 1, which is 5. Again, basically the function notation, you're just replacing x with a value, and negative 5 there. So certainly, probably more often than not, as we work throughout the course of this year, you're more likely to see function notation f of x equals than y equals. As you get into higher level math classes, it's more common to see the function notation used. It's not always just going to be f of x. You may see other letters here, g of x. So the main thing you do have to be careful about with g of 2 here is make sure that when you plug your 2 in, you do not square the negative as well. So that's negative 4, 8, and 1, so 5. Now for this one, g of w. Sometimes you will plug variable quantities into the variable itself. Well, here that just becomes negative w squared plus 4w plus 1. Probably more common is to actually plug in something like this g of x plus 3, which again, here is where you do have to be a little bit careful about how you approach this algebraically, because we are going to need to FOIL. So if you want, I'll write x squared, 3x, 3x, so 6x, and 9. Distribute the 4. And then negative x squared, negative 6x, negative 9, 4x. I'll go ahead and combine those. And then our end result, negative x squared, negative 2x, and positive 4. Don't worry about trying to go back and factoring this. I know sometimes we'll see that step wanting to be done. I mean, there's nothing wrong with it, but when all you're doing is, working with function notation, you can stop there. All right, example 5 is a piecewise function. Again, I know, I think in Algebra 2, you do look at these towards the beginning of the year. F of x equals x squared, plus 1 when x is less than 0, or f of x equals x minus 1 when x is greater than or equal to 0. Basically, what these do is these are your domain restrictions. So if you were asked to find f of negative 1, well, x here is less than 0, so negative 1 squared plus 1 is 2. F of 0 now, x actually is 0. 0 minus 1 is negative 1. Now, f of 1, well, 1 is greater than or equal to 0. And certainly, like if you were taking a quiz or a test, I would not need to see this work. I'm just letting you see kind of which one it's being plugged into a little bit easier. So, that is a little more with function notation. All right, coming back to something we've talked about, with restrictions. Now we're going to even talk about what those restrictions involve as far as the domain goes. So, for 6a, f of x equals 1 over x squared minus 4. Well, first thing I'm going to do is factor our difference of squares. Our restrictions are that x cannot equal positive and negative 2. Now, as far as what that does in terms of your domain, every value but 2 and negative 2 will work. So, our domain starts from negative 2 or I'm sorry, starts from negative infinity. It stops at negative 2 because it cannot equal negative 2. We use parenthesis. Then to include our next interval, we'll use a union from negative 2 until positive 2, and then one final interval from 2 to positive infinity. So there is the domain for example 6. And one final example, f of x equals the square root of x. Again, I know we've talked radicals have to be greater than or equal to 0. Well, if you want to solve this, square both sides, so x has to be greater than or equal to 0. So that puts our domain at 0 to infinity. Something like example 7, where let's say they just give you a list of ordered pairs, negative 3, 1, negative 2, 4, 0, 3, 1, 5, and 4, negative 1. Well, here your domain is, and this is one thing that's a little different. If you just are listing values, because these are the only values we're going to include, we use the, squiggly bracket. So negative 3, negative 2, 0, 1, and 4. So that's how you work with domain if you're just, creating a list of numbers. Example 8 actually has some components of two different things. I know we're going to talk about from, example 6b. For the square root of x has to be greater than or equal to 0. For the denominator of x minus 6, x cannot equal 6. So here is where our domain will put together these two issues. So our domain's going to start at 0, again because you can't divide by 0. It's going to stop at 6, and then after 6 again, it will go to positive infinity. All right, for example 9, this one's probably going to be the most complex of these that we look at. Again, anytime I'm working with radicals, I do like to go ahead and square both sides. So 4 minus x greater than or equal to 0. Now, I'm going to go ahead and factor this. It is a difference of squares. It's 2 minus x, 2 plus x, greater than or equal to 0. Now, we're going to use this term throughout the course of the year, and I'm even going to set up a number line here. And we're going to talk about what are our critical points. They are the values where you have zeros. Well, for 2 minus x, where does this equal 0? Positive 2. 2 plus x, negative 2. Now, from here, what we are going to do is we can plug in some values to determine whether this is greater than or equal to 0 or not. If you pick a value in between, like 0, well, if I plug 0 in for x, I get that 4 minus 0 is 4. The square root of 4 is 2, so 2 is greater than or equal to 0. That's true. Now, what you can do, also plug in a number to the right and left of each critical point. If I plug 3 in, 4 minus 9, well, that's negative, so certainly not greater than or equal to 0. If you plug in negative 3, 4 minus 9 is again negative. You can't take the square root of a negative, so that's also false. So here our domain goes from negative 2 to positive 2. All right, one final example here. If you have something like a formula, the volume of a sphere, V, or volume, equals 4/3 times pi r cubed. Well, it is a polynomial, but unlike a regular polynomial where the domain would just be negative to positive infinity, Well, if you are working with a sphere, you certainly can't have a sphere with a radius, which is what r represents, of -4. You also can't have a sphere with a radius of 0. So the radius has to be greater than 0. So the domain actually is 0 to, in theory, we'll use infinity. I mean, obviously, you can't have a sphere with an infinite radius, but that value can keep getting larger and larger. So that concludes the first half of section 1-2.